Hi guys, good morning. In this video, we're going to see the problem sum root to leaf numbers. In this video, I'm going to show you three approaches for this. One is recursive, one is iterative, and the last one will be from Morris Traversal Preorder Inorder. I'll explain both of them in detail. So yeah, if you guys like the video, maybe if you have watching and if you guys like in the end, then please do the like button. It helps me motivate a lot. So yeah, before further ado, let's start with the problem. The problem says that we are given a root of a binary tree containing only numbers 0 to 9. Cool, no worries. And each root to leaf path is a tree represents a number. So basically, if I just move on from root to leaf, so it will be representing a number. We'll show how. Let's say if the root is, let's say 1, after that another node is 2, another node is 3, then it will just represent the number 123. Cool. We need to return the total sum of the root to leaf numbers, all of them. And basically it just says that, okay, whatsoever answer will be made, it will fit in a 32-bit integer. So we don't have to worry about, okay, if the number becomes very large, because 1, 2, 3, 4, 5, 6 number can go up to so long. But it says, okay, it will fit in the integer. So no worries. Let's see the example very quickly. It says that we have a current sum. Okay, it says that we have this number, let's say 1. After that, we go on to 2. So basically, it was 1. Then another 2 got added. So it became a 12. 1 from above, which is green one, and 2, which is a blue one. So it's a 12. And it's a leaf node. So we just add it in my total sum, which is this 12. Here also, you can easily see that as at the root node, the green one, it was 1. Now it went to 3. So 3 got added. In total, it got 13. So as you can easily see, it got 13. Thus, we added, and it's a leaf node, so we added in the current sum, in the total sum, and we got 25. Let's see another example very quickly. You can see green, its root node, which is 4. Then I moved on to its childs, which is 9 and 0. 9, you can easily see, from 4, it got this 4. Here, it will got the 4 here. And 9 as itself is a value 9, so it just gets added in that 4 9, which means it is 4 into 10 plus 9, or kind of you can say just a calculation of value 4 9. It becomes 49. So it became a 49 and it became a 40. And as it's a leaf node, so I just added in my sum called as a total sum. And here it's not a leaf node, so I will again go in its leaf. You can easily see that 49, it comes from above, 49 comes from above, and 5 is the value here, 1 is the value here. So the value now becomes 495, which is this value. The value here becomes 491, which is this value, and thus we added these values. Cool, no worries. And in this video, I'm going to show you 3 approaches. The last one will be the more optimal one on paper, because it depends on the test case itself. If it's just very complex, so it can be like in runtime, it can show, okay, it's giving actually more runtime, but actually it is the most optimal algorithm. Cool, let's see and how we moved on to the iteration of the example itself. Now it's exactly the same how we are going to do this problem, which means that firstly I will have this as a current sum. Cool, no worries. As I go on to every node, I'll just keep on updating my current sum. How? As I am, let's say on this node, current sum earlier, initially it was 0. So 0 into 10 plus 1. Why into 10? Because we know the next number will be kind of appended in the end. When we want to append any number, we have this number and we want to append any number to the end. What we do is we just shift this number by one place. One place means one digit. And how to shift? Multiply by 10. And then add this number, which is, let's say, x. Then I just added x, so it just comes here. It's the way to just shift one number and append one number. Cool. I just did a current sum into 10 plus that sum node at which I'm standing right now. Cool. I get the current sum as 1, and as it's not a leaf node, so I just can't push it in my total sum. Cool, no worries. I'll just go on. As you can easily see that I just went on to its child, and the child know, okay, what's my parent sum? So now what will happen is, green one, as you can easily see, it's the current sum. I do into 10 because it was previous sum, which was 1 right here, as you can see, 1 sum right here, as you can see, into 10. Then I added the value at which I'm standing right now, which is, let's say this value, if I'm standing at the current node, so it's current node's value. So the new current sum becomes current sum, which was earlier, which was the sum right here, into 10 plus the current node value. It becomes a 12. And same goes here. Although in the case of 2, it's not a leaf node, so it will not get added in my total sum, but it's a leaf node. So I can easily add this in my total sum. As it's a leaf node is just left and right is null. So I can just add it in my total sum, which is the sum. But as you can easily see that it can still go to the left and the right. So it will go to the left, which means my 2 will go to the 4. The current sum at 2 was 12, which is this 12. I just theta into 10 plus 4 to get the new current sum, which is kind of appending that value 4 to the above value, which is 12. I got a 124, and here also I just moved that same thing on to right. I get a 125. It's a leaf node, so I can just easily add it in my total sum. It's not a leaf node, cool, no worries. I can just go on further down. Still I did the same thing, current sum into 10 plus value at this node, which is 6. I get a 1256, and then I can just still add a value. By this, it's just that we have to do in the whole problem. I'm standing at the road, I have this current sum as 0, cool, no worries. Then I'll just ask, okay, what's the sum of the nodes in total? Give me. It will give me. How it will give me? Firstly, in a recursion, everything. See, we just have to trace back the recursion now. How? In a recursion, we have a base node. What if the root is null? Simple. Very, 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 very basic condition. Or also you can have a basic condition that, okay, if left and right are null, just return that sum. But it's very easy that if the root is itself null, which means the left child, right child, or any node is null, I just return number 0, because it will just add a 0 in my sum, right? Cool. If it is not, which means that I just actually have the iteration in the condition, because see, recursion is nothing but base condition, some condition, iteration kind of, and then a recursive call. So this is a condition right here that, okay, as I'm going on to a node, I just find the current sum now, which is current sum earlier into 10 plus that root value, current sum into 10 plus that root value, which is I'm standing right now. And ultimately, if I see, okay, if both are null, which means it can be added in my total sum, so I just right now add it in my total sum. When I say I add it, it just means that I return it to my answer, which will ultimately go on to here, and it will actually be returning my total sum. Understanding how recursion works, it just returns a value. I'm not adding it directly, it just returns a value, which will indirectly get added to the total sum, which will indirectly be returned as a total sum. Cool. Then after that, the recursive condition comes, move the same thing to the left, move the same thing to the right. I just moved to the left node. I just passed that current sum which I have obtained so far to my left child and my right child. And thus, I can just go on iterating at this recursive condition and I can just find my answer. That was the very, very, very easy recursive part. Let's see the iterative part. It's also pretty easy. It's just that we have to just trace back down what we saw in recursion and also in the above explanation. It's the same, we have to trace it down to the thing. How? We are iterating on every levels, right? Because at every levels I was just seeing, okay, what's the current sum now? What's the current sum now? Because I was iterating at level 1, after that level 2, after that level 5 or level 3, level 4, right? Same thing. If we are iterating on levels, so it means that it's a BFS. BFS means we have to use a queue. Same logic applied here, as same as that. We had a queue right here. Very simple. We pushed the first node, which is root, and its sum is nothing but 0. As I said, current sum initially is 0. I just iterate on this root. I just find, okay, what's the first value of this root, like node of this BFS? I just find the current sum now. Same as we did here. We just found the current sum. Then we checked if this is null, right? Left or right or is null or not. Same. If left or right is null, I just add it in my total sum. As it is an iteration, so we don't have to return something, because we can directly add in my total sum. I just did the same thing. And ultimately that call to the left and right child, now it's not a recursion, so it can just be a iteration call, which means I have to manually push it in my queue. And same thing, exactly same thing, root left and the current sum, I'll push it in my queue. And thus I can lastly return my total sum. So it was the BFS part. I hope that you guys understood it very clearly. Now let's move on to the most interesting thing, which is the Morris traversal. What will happen with this is that we can do the same thing in O of 1, which means O of 1 space. Because see, now we were iterating on this whole stack tree, right? O of n time is for sure because we are iterating on every node, but it's also O of n space, which is kind of O of h, which means h is the depth. But if it's a skewed tree, which means if it is one side only, so it can worst case go up to O of n space, because it's queue, it's stack, which means recursion is kind of a stack in backend. So it's kind of that, okay, it will be implemented in O of n space, but because of this Morris traversal, we can do it exactly same thing in O of 1 space. Let's see how. Firstly, what we do in this is, we just see, firstly you will say, okay, Aryan, how would I actually intuit it in the interview? How would I know? So basically, the first thing that what it actually does is it uses a concept of threaded binary tree. And what is that? It is just that, okay, it can reach back to my root node directly from the leaf. And how will it help me? So firstly, what it means is that, okay, my leaf is pointing back to my root. My leaf is pointing back to my root. I'll show everything at how it's made, how it is done. But firstly, we are thinking, okay, why we are actually, what's the firstly using of these threads? Like why it will help me? Why I want to do it, and how it will figure, like how I'll figure out, okay, it can do the same thing in O of 1 space. That's the reason, right? If we want to do O of 1 space, which means that at every point we need to make sure, have we traveled the left part or the right, and we have to travel the right part. Have we traveled the left part or not? Which means that it will help us to know that, okay, if the left subtree have been computed or not. How? Let's see. So basically what we do in a BFS or in a stack, we just do one thing. We just push in, let's say if I am at the root node, I'll push in the left node and the right node, which will ultimately help me. Okay, I'll just go on to iterate on the left node's child. When it is completed, then I'll just go on to iterate on the right node's child. It is what a BFS does in simple words, right? That's the reason here this queue comes in picture. We are storing left node and after that right node. Why we are storing right node? Because we know when we are completed with our left node, we have to make sure, okay, what was the right node I need to go on? Which means that if I'm standing at my 1, if I've completed this whole part, at instant point I should be know, okay, I need to go to 3 right after that, because my 1 is done. I have iterated on the left part. As soon as I'm completed with this thing, which means I have completed 4, 2, 5, 6, I should know I have to move back to 3. Here the interesting part comes of this thread. What will happen with this thread is, as we are completed at this part, the thread will help us. Okay, Aryan, my thread at 6.21, which means that after 6 is done, I have this root node which is 1, and as it is done, which means after 1 you can just move to 3. So my 6 helped me to point back to my root node, which helped me to move to right, because roots left is this part, right is this part. I just want it when my left is completed, because if I am at 6, my left is completed, right? If it is completed, I have to move to right now, and to move to right, I just point it back to root. My root pointed next, which means it's right. By this we will help, okay, how it's actually happen and how we will actually can move to the right. You got, okay, why we are using that thread and why was actually it needed and why it can reduce our space. Because why the space was needed, because we want to move to right. And by just using these 2 pointers, which means the pointer at the head and the pointer at this point, we can just move directly to the roots next. We will see exactly how it is done. Firstly, a few conventions. The current, whenever I am marking in pink firstly, and it denotes that particular root node. Previous, it's for sure marked in green everywhere, and also we make sure that my previous indicates my roots just left extreme right. My roots just left extreme right. That is my prev. My CS is my current sum, my D is my depth. Cool. Let's see how it is done actually. So whenever I am standing at my root node, I have two options. One is, if my left is null, then for sure I will go on my right. Cool. Other option is, if my left is there. Now you will say, Aryan, you saw above, right? Your left was there, but you are confused. Were you like you have to go to left or you have to go to right? Because you had your left, but still you are not sure that okay, you have to go to left or right. So if you have that left, then you have two options. Is your left already visited, or you have to visit your left? If it is already visited, which means that it would be having that thread and we just have to remove that thread. If it is not visited, which means we are visiting for the first time, then we will go mark the thread. I'll show how. Firstly, I am at this current. So basically here I can, like I will just explain, so I will not use any colored thing. I'll just put everything in white. But yeah, it's for explaining. But further you can see everything down. Firstly, I have this current. What I need to do is, my left is not explored right now. Cool, no worries. What I have to do, I have to go to my left, current's left extreme right, current's left's extreme right, and I have to mark it back to my root node. Okay, it's done. Now I can easily move to my left. Now what I will do is, I will just have this current. I'll just go back to the left, current's left extreme right, current's left's extreme right, which is kind of null. So I just don't have to do extreme right, but left is the endmost point. I'll point back to the root node. Okay, cool. Now it's done. Now I have made my particular how my tree should look like. Now I just pointing here. I'm pointing here 4. So basically, if we start back again, okay, we were having this current, we were not having this, we were not having this. It was the first time it was being visited. Cool. Then I just point back. Mark my words, it was the first time it was being visited. How I know that? Because I just went to my left and its extreme right, and no pointer was there. Which means that I just marked my pointer, and I also know as no pointer was there, so it was the first time it is being visited. So it is the first node of my pre-order traversal. Cool. I'm just iterating in this problem. You are not needing that order pre-order, but I'm just iterating, okay, how the pre-order works in this. Then I just move my current. Do we know it's the first time it is being visited? Let's try, see. We move to our previous extreme right, which is kind of nothing. So I can just see, okay, there is no pointer right now, which means I'll have my pointer back to this point current, which is the root, and I'll just push it to, because it's the first time it is being visited, my 2. Cool. And after that, I just moved back to my current here. Now you can easily see, okay, it's the first time it is being visited because left's extreme right, because left is not there, the extreme right is also not there. So it is first time it is being visited. So I have this 4 right now because it's the first time it is being visited. Now, as it has this right, it has no left. So I can't go left because option 1 was go left. If the left is null, okay, go right. If the left is null, go right. So I just moved right, and I can easily move right because I have already made a pointer here. So I'll just move right back here. But I am standing. I just moved right here, right now, right. I am standing at the current now, right now. But still, if we are back to square one, we have to move to left or right. How to know? Let's know right now. How? We will again go back to left and see, is there any node pointing back to me? There, if you go to left and the extreme right, it's already pointing to me, which means that the left part has already been visited. So firstly, I'll make sure, okay, I'll just remove this pointer I'll just remove this pointer and I'll just move my current to my right. By this, what happened was it was not visited. The 2 was already visited, so I just moved to my next. And how I knew that I have to visit right? Because I already have a left thread earlier. By that, I have my current now. Okay, no left, cool, no worries. Case 1, I just move to right. Okay, I just move to right, cool. My current is pointing to here. Now what will happen is, again, no left, so I have to move to right. Cool, I just move to right back. Again, I am in a dilemma. I have a left, I have a right. Where to go? No worries. In the left, you see, left's extreme right. Is there a pointer at the extreme right? Yes, and it's pointing back to me. Oh ho ho, which means that it's already visited. It's already visited, which means I can't push it. See, 5 and 6 will actually push it here. It's already visited, so I can't push it back in my pre-order thing, which means that it has been visited and it's not a new thing. It's not a new thing, which means that I have to remove this pointer. Cool. I have, the current was here. It was already visited, which means I have to visit right now, which means I will move this current to right. It's new thing. Cool. Because everything like nothing has been there. Left and right is not there. Cool. No worries. I just push it in my pre-order. By this, you can easily see, okay, I had this current here. I just went to left, right, made the thread. Cool. Now it is visited. I just again move to my left, and then I just say, okay, move to left, and then again put the thread. I just again move to left. Okay, cool. I just again move to left, which is my current comes again here. It just is gone. But we already saw, okay, we have to think, okay, we have to go to left or right. We can't go left. Why? Because the thread was actually already there, which means in my last traversal, I would have placed a thread. So now I should remove that thread and I should move to right. So I just have the current here. Now I just move to right again. Here the thread is there, so I just move to right. Here again, I have to think, okay, I have to move to left or right. It's the left, it's the right. Left already has a pointer, so I remove that pointer and again move to right. Here I just move to current. It is the whole Morse algorithm. Let's trace it down to our problem, how it can be used in our case. I know the time has been, but yeah, it's now we can trace the Morse algorithm on our problem, which is Morse Traversal, the pre-order one, which you understood right now. Cool. So firstly, my current, see, everything now from now will be colored, so you will get very clear understanding. My current, but now I can use a white pen for showing. My current is actually here right now, right? My previous will just help me to go to the current's left's extreme right. Previous will be here, it will go here, it will go here. It's a left's extreme right. Extreme right has no, it's null right now, right? So I will just mark my thread from previous to this current, which is this thing. Also, at this point, I have found, okay, what's the current sum like, which is in yellow, I showed you, right? So current sum is here. My current has been calculated because I have just put my prevs and then extreme right, move to prev, and then my prev is pointing, my prev's right is pointing to my current, which is the root. Okay, cool. My current is done. I can move to my next node, which means I can move this current to the current here, right here. Now my current will move right here. From here, it just moves to here. Now my current sum, which was 1, it will now become current sum into 10 plus my new root value, as we saw in the recursive and the BFS approach. Cool. My current sum now became 2, but now still I have to do the same thing which we did, which means my prev is pointing to my current's left, and then I just have to move this prev to the extreme right, which I can move. But as there is no extreme right, so I can just put it here only. And as my prev has no pointers pointing, so I have to point my prevs right back to current. I just pointed it back. Cool. My current, it just moves again to left, so my current is pointing here. I just found the value of current, which is nothing but current, existing current into 10 plus the new root value, which is 4. It is 124 now. Cool, no worries. Then I have, as there is no left, so I have to move to right. Cool, no worries. I just moved to right. I just have my current from here, it just moved to here. I'm standing at this my current node, but now I have to think, I have to move to left or right because left and right both are there. I just moved to my left again and saw, okay, my 4, which was my left extreme right, is actually pointing back to me, which is 2, which means that it was already visited. So first thing I can know for now, okay, it is pointing to 2, which is back to me. I cannot move to left. One thing I'm sure, I cannot move to left, but I have a few pending work remaining, which means I have to remove this thread. I removed this thread, which was from 4 to 2. And also, if the thread is moved, which means that 4, it became a leaf node, because earlier it has this node, so its right was not null. But now its left, which was already null, and its right, which was after removing this thread, it became null, which means the 4 became a what? A root node, which means that I'll just push this value, which means the current sum value, in my total sum. And after that, I need to find the current sum again. How I will do? When I was iterating on this current sum to find, okay, if its left extreme right have a thread or not. Meanwhile, I was also calculating my depth of this node. Left extreme right, which means the left of this node 4, I was also finding in comparison to this current, what is the depth of this node. What will happen is, I have this current which I added in my total sum. What I will do now is, I'll just find this new current sum by the existing current sum upon 10 raised to power, here is the depth, which will give me 124 by 10, which is 12, which is the new current sum. It is how I found my current sum of my root by the help of my child. Right? Cool. Now, as I know that it had that connection, I removed that connection, I found my new current sum of root. I also have to move to right. Good. So I just moved my current sum to right. From here, it just moved to here. Cool. Now my current sum from here, it just moved to here. Again, the current sum will be updated by 12 into 10 plus the new value, which is 5. It became 125. Current sum was here. It just moved to here. Again, the value updated to 1256, same as above. Now current sum was here. It just moved because no left, so it has to move to right, and right is pointing to back to that node 1. So my current moved to this node particular right. Now what will happen is, I am standing at this current which is 1. I have still not sure left or right. What will happen is, I'll just go to prev, which will go to the extreme left until it find either it is null or it should be pointing to the actual 1. It is pointing to the actual me. Matlab, its left extreme right is pointing to me, which means that I have this node as visited earlier, which means that it was visited earlier. I have to remove this thread. First thing, I remove this thread, and I have to do a few work also, which means that now this thread is removed, so it's for sure have become null, which means its left and right is null, which means I have to push it back this current sum. And when I was calculating this left's right, I was also finding its depth, which means here the D is 1, here the D is 2, here the D is 3, which means my D has become 3. So my current sum now for this root node has also become a 1246 upon 10 raised to power 3, which is actually nothing but 1. By this, I found out the current sum of my root node. And also I know, okay, I have removed the thread, which means I have to move to right. Here, my current, I just moved this to right. Here, my current came. Now, I just do the same thing, which means my current, it came from here to here. My current sum was 1. My new current sum is 13. Its left and right are both null, which means it's a leaf node. So I can just push it in my total sum. And that is the whole problem which we have to see. I hope that you guys understood it. Let's quickly see the question. Algorithm, sorry. It says that firstly, if I just showed you, right? It has mainly cases are 2. If the left is null or if the left is not null. If the left is null, I can just find the current sum and I can just push it in my total sum if and only if both the left and right are null, which means both the because see, left is null, so I just have to say, okay, if right is null, so it's a leaf node. If it's a leaf node, I just push it in my total sum. And also I have to move to right because left is null, so I can only move to right. Cool, no worries. The case 2 was, as I showed you, if the left has some value. In that, we had major 2 cases. What was the cases? That, okay, I just moved on to my left extreme right and it's pointing nowhere, which means it is not pointing back to me, which is the case 1. And another case was it's pointing back to me. It's pointing back to me, so I have to do many operations, which means that I have to firstly remove that thread. I have to also mark the total sum because now it has become a null after removing this thread, right? I also have to update the current sum of my root node, right? I also have to move my current sum to right. So it is the operation which we have to do when we had this thread, and we have to actually see, okay, if we have to go where. And if it is null, which means I have not gone to my left side, I'll just go to my that side, which means my pref will firstly point to my current, which means making that thread. I will find the current sum value, which is that value, which we very easily find. And then I also know that, okay, I have not gone to left, so I move my current to left, this current. Here you can see, I just move my current to left. Here I move my current to right because I knew that I have visited my left. Thus, in this case, the complexity of this problem is O of n. O of n to iterate on, see, this O of n is to iterate on every of that node. But this O of n, extra O of n, is for that while loop, which means that for every node, I just check, okay, what's the extreme left? And then I was moving to the extreme right. So for every kind of node which has that left part, so I was just moving to the left, which means there's the node right here. I will just go on to the pink thing. For this pink node, which is this like white one which I mentioned, for this, the extreme blue will happen. For this blue one, which is white one right now, the extreme green one happen. So for every specific node, which means one node for the pink, one node for the green, one node for this white, the pink thing, the green thing, the blue thing can happen, which means that this while loop in total will go up to O of n, which is kind of O of n only in complexity terms, or in O terms. So it's the reason its time complexity still remains O of n, while we are not using anything extra except these 4 variables. So it's just space is O of 1 thus. And it's very simple to just have a preorder or a inorder traversal. See, what we showed above is exactly a preorder. In this, I can just write a preorder, which means I can just push in the values here and here, which means I'm just pushing in the values as I showed in the iteration also. And it's the same thing, exactly the same code as you saw above. It's exactly the same code. In order, I did nothing change. It's just that here the name is changed, just the name is changed. Here it's exactly the same. Here in the in order, what happens is that it is left, root and right. So basically the thing which was right here, earlier it was right here. It was happening earlier, which means that one step was happened and I was pushing it here because my root had come first. See, it just indicates that, okay, I had not iterated my left child. It just indicates I have iterated my left child, I have to go to right. Left is not iterated, left is iterated. It just shows. So earlier I was pushing my value node here. But now what happens is my left has already been gone because left is done. Because in order, left is done. Now I have to push it when my root is there, which means after left I have to push. After left I push, which means I push it here. And it's the same thing in order. So yeah, I hope that the video has gone a bit length, but in this I just showed examples of both preorder, inorder. I just showed both the codes, both the intuitions. The example of preorder traversal, Morris traversal, how it can be used in a problem statement, how it is actually helpful, because algorithms we learn, but the examples we don't. So it's an example of Morris algorithm. I will not waste much time, but yeah, it was all. If you guys like the video, then please hit the like button. It helps me motivate a lot. And yeah, see you guys in the next video. Goodbye. Take care.